Hi everyone, am I audible? Okay, great. So let us start. So we will try to finish trees, and then maybe at the end of the class, we'll also try to start a new topic. But how many of you got time to solve questions that we discussed in the class yesterday? You can say yes if you were able to do that. Okay, so out of all the sessions that I have taken so far in past 3 or 4 years, I have seen there are three kinds of people. First kind of people is that which comes to a class, attends the class, understands everything, feels everything is doing great, feels everything is going great, but they do not solve question. The second category is that which does what the first category does, but also solves the question. And the last category is that which when feels that things are getting tough, simply runs away. So I want you guys to lie in the second category, where you attend the class and solve the problems also, because that is the only category which succeeds. Everything else is just like a bubble. I mean, it has no value at all. Okay, cool. So we will just start now. So with every data structure that you would have learned till now or you will learn in future, there is an important operation called as traversal. Okay. What is the meaning of traversal? What is the dictionary meaning of traversal? Traversal means traveling. Yeah, you can say that. So you must have been asked by someone that I'll give you an array. So let's say there is an array which contains some integers like that. And now you have to traverse the array. So traversing the array simply means printing the contents of this array from left to right. Now it is super easy to print the contents of array from left to right. You can just have a variable I equals to 0, and you can make this variable go till n-1. And every time you can print array of I. That's it. Cool. So this is an iterative process which can be accomplished using a for or while loop, whatever you like. But if we have a tree which is not a linear data structure like an array, then what to do? For instance, you have a tree that, let's say, looks like this. Okay. Can you traverse this tree by using the same iterative technique? The answer is no, not exactly the same, because tree is not linear. So how do you decide in which direction to go to? When I say direction, let's say somebody gives you a pointer to this, and that pointer is P. Now, there are two directions that this P can be made to move into. So either you can make it to move towards left, or you can make it to move towards right. Here your eye is always going towards right, which is in the forward direction. But here you'd be a little confused. For instance, if you are here, you can print P arrow data, which is 5. And after that, where to go? So let's say randomly, you decide to go to left. If you decide to go to left, you will change your P to something like this, P equals to P arrow left. In that case, from here, you will come here, and then you can print this 3. I would say there is a big mistake that you have made by changing your pointer from here to here. That big mistake is, now will you ever be able to go in this region? Will you be able to do that? Yes or no? The answer is no. Why no? Because if you have come from here to here, you came from here to here because there was a directed edge. Pointers are like a directed edge. This node was pointing to 3, but 3 is not pointing to 5. 3 is not pointing to anything else in this part. So there is no way you can go back to that subtree. So that is the greatest problem that happens with hierarchical data structure. So in hierarchical data structure, you can't just expect to keep moving in one direction, because it is not unidirectional, it is multidirectional, right? So in this case, what to do? How to traverse such kind of trees? What can be our go-to approach? Think about it. Okay, so one of you is saying as we have single source and multiple destinations, so we can use recursion. Okay, cool. Others? Yeah, now it's very natural to say that we will use recursion because all the problems that we have solved so far in trees, they have been solved using recursion only. Okay, let's talk about it. So we'll think very, very fundamentally, guys. Tell me one thing. The biggest problem over here was that when you came from here to here, you forgot about this part. So I don't want to forget something. How to ensure that I do not forget something? So think about something like recursion. When you use recursion, what happens? Let's say there is a recursive function f, and you have called this function f for your overall root, which is 5, for example. Correct? Now, what you can do is, because you are at this node 5, you can easily print it. So let's print this 5 and feel great about it. Okay. And after that, what you can do is you can make a recursive function call for the left child of 5. What is the left child of 5? That is 3. So you can call this function f for 3. And once this function is over, then you can call f of 8. Now just wait here, just hold on. Printing something is very easy. When you are at a node, you can easily print it. Now, when you are calling a particular function from a different function, let's call this parent and let's call this child. When the child call is over, the control comes back to the parent. You understand this? So let's say main function calls another function sqrt. When sqrt is executed, control comes back to main. So there is a coming back which is happening. So once this is over, control comes back here. And because control comes back here, you have the flexibility to call that, which was not happening in a normal iterative approach where you were changing your pointer from p to p left, because there is no way to go back. But recursion allows you to come back. So if you came from here to here, once you have printed this, you can come back from here to here and make those calls. This is the fundamental reason why recursion will be supported here. Is that making sense? Correct? Okay, great. Now, there are different ways in which you can traverse this particular tree. In fact, somebody asks you to traverse, let's say, an array, then you can traverse it in different way. Like you can traverse it from beginning till the end, which is you can print 2, 1, -1, 3, 0, or you can traverse it from end to the beginning, which is you can print 0, 3, -1, 1, 2. Similarly, a tree can be traversed in different ways. Okay, so although there can be multiple different ways of coming up with different traversal sequences, but 3 of them are most popular, and you might have heard of it. They are called as pre-order, in-order, and post-order. Order just means sequence. So these are the 3 most popular recursive tree traversals. They can be implemented iteratively also, but their recursive implementation is super, super easy to understand. So we'll talk about that first. Anyone who's already written code for these 3 kind of traversals and knows how it works? Okay, so let us all understand. See, if you understand these 3 things, if you really understand these 3 things conceptually rather than mugging them up, then it will be very easy for you to solve most of the questions on tree traversal, because they are just based on these techniques only, most of them. Okay. So what is pre-order traversal? Let us understand that. Pre-order traversal says a very simple thing. It says that, let's say we have a binary tree. So binary tree will have a root and a left subtree and a right subtree. The pre-order traversal says if you have to traverse such a kind of tree, the first thing you should do is you should print the value present in this root. So whatever is the data or value present in this root, you print that. And after that, you should print the entire left subtree, which is after that you should traverse the entire left subtree. And after that, you should traverse the entire right subtree. So basically it is saying that traversal of the complete tree is equals to this thing. according to pre-order. If you have to traverse the entire tree, then you first print the root, and then you print the entire left subtree, and then only you print the entire right subtree. This is all that it says. Now here you might be wondering one thing, that hey, printing one node is very easy, but what do you mean by traversing this left subtree and traversing this right subtree? So this is recursive. You can say that traversal of a huge tree is dependent upon the traversal of two smaller subtrees. So things will happen in a recursive manner over here. So the first instruction that you will execute in your code whenever you are at a node is to print that node. The next instruction will be to recursively make a call for left subtree, and the final instruction will be to recursively make a call for the right subtree. Those of you who are new to it, are you getting a hang of how recursion can ensure to print things in the right manner? Yes or no? Or can you just go ahead and write a recursive code for this? Okay, so let us try to understand that. I'll take a quick and easy example. So let's say we have got this tree. Okay. So how are the things going to get printed according to this? Let's understand that. So you will first make a function call for your root, which is 5, f of 5. Now, whenever you are at a node, what is the first thing that you do? According to pre-order, what is the first thing that you do? You print it, right? So you will print this node 5. You have printed it. Mind it, that's your first node to be printed. Let me write it here. Okay. And after printing the node, what do? What is the next instruction? Just look at it. It's written on the board right away. I'm not sure why some of you are not able to answer that. If it's written on the board, you should be able to answer, right? You print the node, and after that, what do? You make the call for left subtree. So what is your left subtree? Left subtree is rooted at 3. So you will call f for 3. And once it is over, then you will call f for 8. This is nothing different from that. I'm not sure why some of you could not respond to it. So you are at a node, you print the node, and then you call for your left, then you call for your right. And now just keep doing this thing on and on and on. So now you came from f of 5 to f of 3. So again, at f of 3, the first thing you will do is you will print this 3, and then you will call for the left subtree of this, which is null. So see, after printing 5, you printed 3. So let me write 3 over here. Now at f of null, you will not do anything, because what is the meaning of f of null? It means that you are trying to traverse an empty tree. An empty tree does not have anything, so nothing is to be done. Again, coming back to f of 3, you had called the left subtree, so now you will call the right subtree, which is f of 4. Again, at f of 4, what will you do? You will first print the node 4, and then you will make a call to the left subtree, which is rooted at 6, and then you will call the right subtree, which is rooted at 7. So after 3, 4 got printed. And now again, at f of 6, what to do? The first thing to do is to print this 6, and then make a call to the left and right. So you make a call to f of null and make a call to f of null. And nothing is to be done over here. So do you realize that here my termination condition will be when the passed node is null? When the passed node is null, nothing is to be done. Is that making sense to all? Yes or no? Correct? Okay. So now this is over. So like now you can say that for f of 6, all the instructions are over. So now the control comes back to the parent, and now this f of 4 makes a call to f of 7. Do you realize it? Whatever has happened over here is what I had actually said. You are at f of 4 and you came from here to f of 6. And now because this is over, control came back to that. And that's the reason you can now call f of 7. So that is what is happening here. Now again, at f of 7, the first thing you will do is you will print the node 7. And after that, you will make a call to the left child and right child, which is you will call f of null. And then again, you will call f of null. Nothing actually happens. Okay. And then this is over, control comes to this is also over, control comes to this f of 3 is also over, control comes to this. Now do you see one thing? When you look at this f of 5, you first printed 5, And here in this part, what you have done is you have printed your entire left subtree, correct? And then the same thing will be done for the right subtree. So right subtree is rooted at 8. The first thing you will do is you will print 8. So let me print that 8. And after that, you will make a call to f of 9. And then you will make a call to f of 10. At f of 9 again, the first thing you will do is you will print 9. And then you will call left and right, which is f of null, nothing happens, control goes back. Then again here, you will print 10. And then you will call f of null. So this is the pre-order traversal of the given tree. You have printed 5, 3, 4, 6, 7, 8, 9, 10 according to this order. Does it make sense? How many of you understood how pre-order traversal works? So if I give you any random tree and ask you to figure out its pre-order traversal, can you do that? You should be able to do that. Okay, so let's take a tree for example. Let's say I'm going to give you 2, 3, 4, 5, 6, 7, 9, and 10. Yeah, tell me the pre-order traversal of this tree. Okay, you know, this kind of question is a very well-known question in MCQ rounds of many company interviews. They give you a tree and then they give you multiple options A, B, C, D. They ask you to tick that option which represents the correct pre-order traversal. So the first way is that you can create such kind of recursion tree, and from that you will get to know that in what order the nodes are getting printed. Second way is that you can do it on a piece of paper in a very simple manner as well. So I'll just show you in some time. But before that, let me take a look if you guys are able to answer it correctly or not. So I can see most of you have answered it correctly. That's great. Okay, one of you is asking, can you please confirm what will happen when node has more than 2 branches? You know, here we are talking only about binary tree. Let me tell you that. Okay. And when you are talking about a ternary tree or a generic tree, then the situations will be different. Then you have to define what is your pre-order. For example, if you have such a kind of tree, then you will have to tell that, hey, first I'll print this, and then I'll print the leftmost, then this, then this, then that. So this is just going to be a generic form of whatever you have learned right now. But I would recommend you to master this thing first and then go to that. Otherwise, you will be confused and you will not be able to learn anything. Okay. So first master this particular thing. Okay. So if you have to, let's say, print the pre-order traversal of this, you start from the root, which is this node 2. Now you'd say, hey, first I'll print this 2. And then after printing 2, I'll focus on the left subtree. The left subtree is this. So let me draw it. And after that, I'll focus on the right subtree, which is that. Cool. So this 2 is printed. Just leave it. Let it go. Now again, for this, you will first print the root, which is 3. And then you will print the left subtree, which does not exist. So nothing is to be printed. And then you will print the right subtree, which is 4, 5, 6. And let it remain as it is. Now again, 2 and 3 are sorted. So again here, you will first print the root, which is 4, and then the left subtree, which is 5, and then the right subtree, which is 6. Same thing you can do for this. You can first print 7, which is root, and then the left, and then the right. So using this, you can very easily extract the pre-order traversal of any tree. It's totally up to you. Everyone can do that. This is the simplest thing that one can ask you to do in a tree interview, tree traversal interview. Right? Okay, great. So now how to write the code for this? I mean, the easiest kind of code that you encounter in tree traversals is for such kind of traversals, pre-order, post-order, in order. So there is a function called as pre-order. it does not return anything. It simply prints the data. So it is void in nature. And what it takes the root node of the subtree which you want to traverse. So tell me, the first thing should be your termination condition. Termination condition comes when the current subtree that you're talking about is empty. If it is empty, then the root will be null. So if root is null, you simply return. You don't do anything. Okay. Otherwise, what is the first thing that you do? The first thing that you do is you simply print. You can use your print command. I mean, whatever is there in your language, I'm just writing a pseudocode. You can print your root data. And after that, you can make a call, recursive call to the root left. And then you can make a recursive call to the root right. Okay. Now, do you see one thing in this traversal? What is happening is first you print. The first statement is to print. The second statement is a call on left subtree. And the final statement is a call on right subtree. Probably this is the reason it is called as pre-order, because this thing precedes LST and RST. Okay. Cool. So that was our recursive code for it. Anyone who would like to talk about quickly talk about the time complexity of this code? Yeah, it will be order of n. Because even if you look at this particular recursion tree diagram, you can say that every node is being touched only once. So you touch a node, print it, and move on to the next set of nodes. So if there are n nodes, you are touching them once, printing them once. Printing an integer is order one affair, so it will be order n. Is that clear to everyone, that how it is order n in terms of complexity? Okay. So after learning pre-order, we will talk about in order. So let us understand what is difference between pre-order and in order. In order, traversal of some tree which is rooted at, let's say, R, is written as, you say that, hey, first I'll print the entire left subtree, which is you will first make in order call on the left subtree. And after that, you will print this root, which is R data. And after that, you will print the right subtree, which is you will call in order for R right. So the only difference is that the pattern over here will be LST will come at first and print will come in between LST and RST. So that is the only difference. So in order traversal, the root is sandwiched in between the left subtree and right subtree. That is how it works. Does it make sense? What is the fundamental difference between in order and pre-order? Can you tell me the in order traversal of the tree which is currently on the whiteboard? Okay, let me tell it again. You understand what is the meaning of left subtree and right subtree? I hope you understand that. So in order traversal, if you have been given a tree, you first print the entire left subtree, then you print the root, and then you print the right subtree. That's it. Okay. Yeah, I'll help you with the output, but I want you guys to try it out. Some of you have tried it already, and looks like some of you are right, others are wrong. So what exactly are you trying to do? Are you able to draw the recursion tree diagram? So your answer, is that just a wild guess, or is that answer written from recursion tree diagram? If you are honestly drawing recursion tree diagram, no one can prevent you from getting correct answer. Okay, let's talk about it. See, it's again too easy, right? Because in order traversal, what it means you will first print the entire left subtree. So let's draw the entire left subtree somewhere, which is 3, 4, 5, and 6. After the left subtree, you print the root, which contains value 2. And after that, you print the entire right subtree. I have done the first step for you. Can you do the next steps for yourself? Just do it, keep doing it in a repeat mode. So again, when you look at this particular tree or subtree, whatever you call that, you will first print the left subtree, which is empty. So nothing is to be printed. After left subtree, you print the root, which is 3. And after 3, you print the right subtree, which is 4, 5, 6. And keep everything else exactly the same. Now again, here, you first print the left subtree, which is 5, and then you print the root, and then you print the right subtree. Same thing would happen here also. You'll first print the left subtree, which is just 9, and then the root, and then the right subtree. So 3, 5, 4, 6, 2, 9, 7, 10. This is the correct output. Is it making sense? How many of you ended up getting this output on your own? Easy, isn't it? Okay. Now, again, if you analyze this output, you will see that the in-order traversal of this particular tree first contains all the nodes of LST, which is 3, 4, 5, 6. 3, 5, 4, 6 actually. Yeah. So these are all the nodes of left subtree. And here in between, you have the root. And after that, you have all the nodes of right subtree. Okay. Now again, when you look at this left subtree, which is this thing, then in 3, 4, 5, 6, first you have printed the left subtree, which is empty, so nothing is printed. And then you have the root, and then you have the nodes of your right subtree. Now again, in your right subtree, you have first printed the left subtree, which is 5, and then 4, and then 6. That is how recursion works, and that is how you end up getting such kind of output. Feeling confident now to predict the output of in-order traversal? Okay, how many of you can write your code to generate the in-order traversal? So the only change that will come is, so let's say you have void in order, and here you are passing the root of a tree. Termination condition will be exactly the same, because if you encounter null, just return. Otherwise, what is the first step? What's the first step? The first step is to recursively call for the left subtree. Very good. So you will recursively call in-order method for the left subtree, which is rooted at root left. What is the second step? Second step is to print the data present in this root. So you can print whatever data it has. And the final step is to recursively call for the right subtree. So you'll call in order for root right. Okay. Can I say it will have the same time complexity that the pre-order had? The answer is yes, of course it will have the same time complexity. Why? Because here again, I can say that we are touching each node exactly once only. The only thing is that the order or the sequence in which nodes are getting printed, that is different, but you are not touching a node again and again, only once. Okay. Cool. The final order of traversal that we should know about is called as post order. And now you can see why this is called as in order, because root is sandwiched in between LST and RST. So now we will talk about post order. Post means last. So post order traversal says that you will first print your left subtree, okay, which is this part, and then you will print your right subtree, And then at the end, you will print the data contained in the root. Okay. So post order gives the final priority to the root. It first prints the left subtree, then the right subtree, and then only it prints the root. I think some nodes are missing from it. Let me redraw that, and then you will have to tell me the output. So I think we had a 3 over here. Yeah, so tell me, what is the post order output of this tree? Okay, 2 of you have given some output. Okay, what do you have to do? Nothing special again, right? So if you take a look, this is your tree. You first want to print the entire left subtree. So draw the entire left subtree somewhere. It is 3, 4, 5, and 6. And then you want to print the entire right subtree, which is 7, 9, 10. And then finally, you want to print the root data, which is 2. Now coming back to this, again in this tree, when you look at this tree independently, you first print the left subtree. Left subtree is empty, you won't print anything. One of you have a question. Can you please explain any one traversal without regression? I'm coming to that. Let us first finish this. Okay. So when you look at this, you first print the left subtree, which is empty, so you don't print anything. And then you print the right subtree, which is this. And then you print the root, which is 3. Okay. And draw rest of the things as it is. Now here again, you first print the left subtree, which is 5, and then the right subtree, which is 6, and then the root, which is 4. Same thing will be done here. You first print the left subtree, right subtree, 7, 2. That's your output. How many of you got the similar output here? Yes or no? Yeah? Okay, great. Cool. So now again, you can inspect it for yourself that post order traversal says that the first set of nodes should be from the left subtree. So you can see that the first set of nodes, which are 5, 6, 4, 3, are entirely from the left subtree. And then the next set of nodes should be from the right subtree, which is true. And then the final thing should be the root. Okay. Cool. Now, if you want, you can come up with your own order, your own different sorts of order. People keep coming up with it. So somebody would say that, hey, let us come up with something called as reverse post order. So in reverse post order, if I define reverse post order, I might say that reverse post order traversal of a tree rooted at R. In that, I'll first print the root data, and then I'll first focus on the right subtree, and then I'll focus on the left subtree. Okay. So can you generate the output of such a kind of traversal rule? Yes or no? Extremely easy. The concept again remains exactly the same. You just have to sequence things properly the way we have done here. Cool. So now let's move on from here. I believe you can write the code for post order. Can you guys do that? Okay. I'll tell you one thing. One of you said that if you want to print reverse post order of a tree, then all that I'll have to do is first generate the post order in an array and then reverse it. Is that the correct way? Think of it. It's not the correct way. Why is it not the correct way? Because, I mean, you can take an example here itself. The post order traversal of this tree looks like that. But if you consider the reverse post order, this 2 will definitely come at the beginning. But after this 2, you will have reverse post order of root right, which is 7, 9, 10. And after that, you will have reverse post order of root left, which is 3, 4, 5, 6. Now, do you understand it that 7, 9, 10 will get printed before this? So there is no way that the output that you would get would definitely be the reverse of this thing. You can even try that out. So again, if you are printing this particular thing, the first thing you will do is you will print the root itself, which is 7, and after that you will focus on the right subtree, which is 10, and then 9. But let's come over here. What do you think? Will here also the situation be the same, or will it be slightly different? Think about that. Same or different? Can you tell me the reverse post order of the remaining part of the remaining tree? Is it 3, 4, 6, 5, or is it something different? 3, 4, 6, 5, right? Okay, cool. We have got 3, 4, 6, 5. Now tell me, those of you who agreed to it, that the reverse post order needs not be the reverted form of actual output, what do you think? Here it comes out to be the reverse form of it, right? I mean, 2 has come over here, 7 has come over here, 10 has come over here, then 9, then 3, 4, 6, 5. So what do you think? Is it just a coincidence, or the approach was right? Yeah. Anyone who can think of a counter example? These are good questions to ask to yourself. Okay. So when you think on these things, when you come up with some counter examples, then you grow. Okay. Take it as a food for thought. Think about it. And whoever has thought about it can discuss it with me. For now, we'll move on. Okay. So you can have reverse of in order also. You can have reverse of pre-order also. That's totally up to you. Those are just different sequences. So you'll get different results, and that's it. Now, one of you had asked that how to do these traversals without using recursion. So my first question to you is, what do you think? Is it possible to do these traversals without using recursion? Yes or no? If it is possible, how can we do that? Okay, so one person is saying we can use a stack. Okay, why do you want to use a stack, and why don't you want to use a linked list or queue or anything else? Yeah, to mimic the recursion. So when recursion works, it internally works by creating a stack of the function calls. So for example, if function f, let's say called function g, it called function h, it called function k, then what your computer does is, in a stack, it keeps on storing these function calls. So first it stores f, then g, then h, then k. And why it does this kind of thing is because whenever a function is over, let's say k is over, then the control can easily come back to h. Whenever h is over, control can easily come back to g. And let's say g wanted to call z, then now it can call z. So it means that instead of letting recursion to create a stack, why don't you create a stack of your own? If you create a stack of your own, then maybe you can perform all these traversals. So I'll give you a quick example of this thing. So let's say we have the same kind of tree, okay? Okay. So what is the first function call that you make? The first function call is always made for the root. And your root is 2 over here, right? Cool. So what will happen over here is that in your stack, let's say there is some kind of stack, this 2 will get pushed. Okay, before all this, I want to ask you a question. Is there anyone who does not know anything about stack? Does everyone have little bit of idea about stack? Yes, no? What it is? So just to let you know, stack is a data structure in which elements are inserted always at the top. So for example, if you have to insert 9, 9 will come above 2. Then if you have to insert 11, 11 will come above 9. So insertion always happens at the top and deletion also always happens at the top. So if you have to delete an element, you cannot go and delete it from middle or from the end. You always have to delete it from the top. That is the only rule of a stack. Okay. Now, yeah, as I was saying, the first function call that you make for any traversal, let's say pre-order traversal, currently we are talking about pre-order, is you call this. So it will be there in the stack. Now tell me one thing. If you are calling pre-order of 2, how it works? It first prints this 2, okay? And then it calls pre-order on the left child of 2, which is 3. And then it calls pre-order on the right child of 2, which is 7. I want to mimic this behavior. Or technically, I can say that, hey, after moving from 2 to 3, if I know about 7, if I remember it that I have to come back to 7, then it will be a job done for me. Because while migrating from 2 to 3, I get lost, I let loose of the sight of 7. So I don't want that to happen. So how can we do that? We have a stack. Now, whatever is at the top of the stack, we can take it out and we can print it. So let's say you take out the element from the top of the stack. In stack, always the element at the top is visible. Nothing else is visible by default. So you take this 2 out and you print this 2. After printing this 2, what you can do is, what to do? Will you just insert 3 inside it? The answer is no. You should not just insert 3 inside it. Why? Because if you just insert 3 inside it, where is that 7? You will lose track of the 7. So what you should do is, you should first push this 7 and then you should push this 3. So let me tell you what happened. Let me tell you what just happened. The old state was something like this. You had 2. So what was the first step that you did? You took 2 out and printed it. This was the first step. The second step was you pushed the right child of 2. The right child of 2, which is 7. And the third step is you pushed the left child of 2. This is the step that you executed. Now, let me tell you why you executed the step in this manner. Because you want the right subtree to be printed after left subtree. Left subtree is at 3, right subtree is at 7. Now, in a stack, whatever is at the top, that is given first preference. Correct? Whatever is at the top, that is given first preference. So when you took this thing out, you should make sure that you first push this 7 and then push this 3. As a consequence of that, it will naturally be made sure that first you operate on the tree rooted at 3 and then only you operate on the tree rooted at 7. So this is what we can do. So using a stack is solving all the problem for us. How? Once you have printed the tree rooted at 3, you will come back to this 7. You have not forgotten this 7 and then you can take care of it. The only important thing is in what sequence to push. So in what sequence to push, I have already mentioned it here. First push the right child and then push the left child. Because whatever is pushed at the end, that will be at the top. And here you want to first operate on left. So left subtree is pushed at the end and right subtree is pushed at the beginning. Is that making sense? How many of you are getting the idea? Yeah, you'll have to tell me what exactly to explain again, and then I can do that. Yeah. How many of you understood it 100% by the way? Whatever we have discussed so far. And how many of you kind of understood it 70, 80%? Yeah, I'll repeat it. Don't worry. I'm just trying to understand like how quick you guys get it. Yeah. Okay. Hmm. Why not think a bit more on your own? I want to give you guys time. I want you guys to make your brain works on your own once. Whatever I have said, munch that for maybe 2 more minutes and see if you can actually relish that idea. Everything is still there on the board, okay? I'll help you recollect whatever I had said. There is a stack that we need. And in that stack, you first push the root. The root here is 2, correct? Now in pre-order traversal, what do? You first print the root. And after printing the root, you focus on the left subtree and then you focus on the right subtree. So let's look at it again. There is a tree which is rooted at some root. Okay. In pre-order traversal, you first print the root and then you focus on left subtree and then you focus on right subtree. Can I say this is all that pre-order traversal is? Yes or no? Yes or no before we move on? Yeah. So we want to achieve the same kind of thing using a stack. So what I'm saying is, let's say you have an empty stack. And in this empty stack, you first push your root, which is 2. Okay. Now, follow this rule. That's it. Following this rule means whatever is at the top of the stack, you take that out and you print it. Now, some of you are asking how to print this too. So if you have ever worked with stack, you will know how to get the top element from the stack. Those are language specific details. I'll write the code. But if you have a stack, you can always get the top element. You can take it out and print it. Okay. So you can take out the top element of the stack and you can print it. And after that, what to do? After that, you should first focus on left subtree and then you should focus on right subtree. Now, what kind of data structure is stack? Stack is a last in, first out. Or in other words, whatever you push first, that will be below the thing that you push second. Do you realize that? Let's say there is a stack of plate. You put plate 1 first and then you put plate 2. So plate 2 will be at the top. What do you want? You want to work with left subtree before working with right subtree. So which subtree should be pushed first? Should you push left subtree first or should you push right subtree first? Think and say. You should push right subtree first, because if you push right subtree first, which is rooted at this particular 7, then this 7 will come below 3, which is your left subtree. So I have written the second step after printing the topmost node over here will be to push the right child, and then the next step will be to push the left child. Is that making sense to all? Yes or no? Correct? And you can go on repeating this process. So you printed this 2. After printing this 2, you pushed the right child of 2, which is 7, and then you push the left child of 2, which is 3. Right? Now again, what is the top of the stack here? The top of the stack is 3. You will take this 3 out. You will print this 3. Now what to do? See, follow the rule. You took 3 out, you printed it. After that, what to do? You will first push the right child of 3. The right child of 3 is 4. You will push that 4. Okay. And after pushing that 4, you will push the left child of 3. Now tell me one thing, is left child of 3 present here? Does 3 have a left subtree? No. So there is no need to push. So keep it in your mind. Push right child of 2 if it exists. Push left child of 2 if it exists. 2 means whatever your root was. So when you printed this 3, you did not push left child because it did not exist. Right child existed, so you first pushed that. Okay. Now again, what is the top of the stack? It is 4. So take this 4 out and print it. After printing 4, what will you do? you will check whether right child of 4 exists or not. It exists, so you will push it. And then you will check if left child exists or not. It exists, so you will push it. Now again, what is the topmost? It is 5. So you'll take this 5 out and you will print it. After printing this 5, you will check whether the right child exists. No, so you won't push. Whether the left child exists. No, so you won't push. Okay. Now again, the topmost of the stack is 6. Take it out and print it. Does the right child of 6 exists? No. Left child? No. So nothing is worth being pushed. Okay. Now what will happen? Now the topmost of the stack is 7. Do you see what just happened? You printed this root. You printed everything that was in the left subtree. And after that, you automatically got access to this 7. Why? Because you had ensured to push the right child after printing this 2. Remember the initial state? Does it make sense? How many of you are able to understand how this algorithm is working? Right? Now again, when you are at this 7, what is the first thing that you will do? Follow this order or this order. You print this 7. Take this 7 out, print this 7. After printing the 7, check whether its right child exists. Yes, it does. So push this 10. And then check if left child exists. Yes, it does. So push that 9. Now, again, what is the topmost? It is 9. So you print that 9. After printing this 9, does it have a right? No. Does it have a left? No. So nothing is to be done. Now the topmost is 10. Print this 10. Does it have a right? No. Does it have a left? No. Now the stack is empty. So the initial state of the stack was empty. The final state is also empty. So you have to continue running this algorithm as long as your stack is empty. Does that make sense? Correct? Okay. How many of you can code this approach? Or at least code the pseudo code? If you don't know how to use stack in your own language, can you? So please do that. Yeah. I'm giving you guys 2 minutes. Whatever you are comfortable with, code, pseudo code, at least try writing it, or at least algorithm, try writing it. Sujay has sent his code. If you want for a reference, you can take a look at that. By the way, this is a very, very common interview problem. Interviewers ask you to print the pre-order traversal of a tree without using recursion. The intent is to check whether you really understand the recursion or not, because recursion is internally implemented using stacks only. Anyone else who has written the algorithm, pseudocode, or whatever? Okay, so we'll write it now. Let us take a look at the board. Okay. The first thing that we need is we need a stack. Okay, so you can create your own stack if you want, but don't waste time in that. Every language has an inbuilt stack. Like you can declare it by saying we need a stack of the following type. So what should be the data type of our stack? I mean, should it be a stack of integers or should it be a stack of node pointers? Yeah, it must be a stack of node pointers. Why? think. It is very important to think. See, if you have a stack of integers and let's say you push an integer 2 inside it, is there any way that after extracting that integer 2, you get to know that what was its left and right child? There is no way, right? From an integer value 2, you cannot figure out what node that 2 was contained in. So you need to have a stack of node star. That is the first step. And give it a name, call it stack. Now, the first step is initialization. Initialization means you first push into that stack the overall root. Okay, so you do stack dot push of root. Okay, and now you have to keep on performing this thing as long as your stack is non-empty. So you will do this in a while loop, correct? So you have a while loop which has a condition inside. What should be the condition? The condition should be as long as the stack is non-empty, just execute the body of the while loop, right? So while not of stack dot empty, you will come inside and you will execute some piece of code. So tell me, what is the first step? They are written in front of you, but want to hear again? What's the first step that you want? Yeah, first you should seek the top element of the stack, whatever is the top element. Let's take that out. So you can do that by using stack.top. This is an inbuilt method on stack. So when you do it, you get access to the topmost node in your stack. And after you have gotten access to it, you can remove it from the stack. So if you do stack.pop, it will be removed. So it's like the first step is almost done. Now what you can do is that you can print the value present in this node. So you can just print node data, whatever it is. So this is like your step 1, which is done. You have taken the top element out and you have printed it. Then what should be the next step? The next step is to push the right child, but push the right child only if the right child exists. So if node right exists, then only you will do stack.push of node right. This is your second step. And the third step will be exactly the same. The only difference is that instead of node right, it will be node left. So if your node left exists, you will do stack.push of node left. This is the third step. That's it. The job is done. This is enough code for whatever we have learned. Is that making sense? How many of you understood what the code is doing and how it's doing? Easy, isn't it? Nothing very, very rocket science about it. Okay. What is the time complexity of this? The time complexity of this will be order n only. And let us understand how. It might not be very easy to guess time complexity from here, but if you change your thought by a certain angle, you will understand how. See, each node of the tree is pushed to the stack once, and it is popped from the stack once. So I can say for each node, you are doing 2 operations. First, you are pushing it, and then later at some point of time, you are popping it. And mind it when I say later at some point of time, because for instance, when you had 2 over here, you had pushed this 7, and then later, much later, you had popped that 7. So when the nodes are getting pushed and when they are getting popped, that is of no concern to me. But what is of concern to me is that for each node, we are just doing 2 operations. We are pushing it once, we are popping it once, and push and pop are constant time operations. So I can say 2 operations are done for each node. So for all the n nodes, 2 into n operations will be done, including their push and pop, and 2 into n is order n only. Does it make sense now that how the time complexity is order n? Correct? Okay, great. Cool. Now let's move on. So mind it that this code is only for pre-order. This is not for post-order. This is not for in-order, right? Step one again. I mean, what is logically your step one? Forget about the code. That code you should figure out on your own in your own language. The first step is that whatever is the top element of the stack, take that out and print it. That's it. If you understand it, then the job is done. Now there are different functions in different languages, like in C++, using stack.top, you get to know what is the top element of the stack. Okay. And after that, you just remove it, you kick it, and then you print it. That's it. Okay. Cool. So let's move to the iterative form of in-order traversal. So we want to perform in-order without recursion. So of course you have to use a stack again, but can you do that? How many of you can now perform iterative in order, given that I have already taught you iterative pre-order? This could be challenging. This could be challenging, but we will learn it in a way that makes it super easy to understand and super easy to extend it to other kinds of traversal also. Like you can use the same concept that we will learn now for iterative post order as well. By the way, any thoughts till now by others? You can just mention whatever random approach comes to your mind for iterative in order. Okay, first of all, do you all understand that this code is not going to give us in order? This is for pre-order. So something has to change over here. Something has to change. Now, what has to change, that we have to decide. Correct? So let's take example of the same tree again. I think it was 2, 3, 4, 5, 6, 7, 9, 10, right? Okay. So tell me, see, in this particular code, which is for pre-order, what you silently did was you took an empty stack and you pushed the root in it. That was your initialization step. You pushed your root. And now what you did according to this code was whatever is the top, you take it out and you print it. This very step is wrong when thought with respect to in order, because in order, you don't print the root first. You print the root only after you have printed the left subtree. So here I don't have the liberty to print whatever is at the top. This is the first thing to understand. Is that making sense? Yes or no? Correct? But having said that, I can say this thing, that this root has to be printed at some point of time. You should not print it forefront, but you should print it at some point of time. Okay, at what point of time? So now you should think of it. When should you print this to? Yes, you should print it after the entire left subtree has been printed. After the entire left subtree has been printed. Now I'll tell you one very important thing. See, let's call it root. Now, if you are able to move on to a state where there are three things, at the top you have left subtree of the root, and here you have root, and here you have right subtree, then the job will be done. See, keep it in your mind. Initially you have root, which is 2. Okay. Now, if you are able to move from this state to that state where above the root there is left subtree, which is 3, and you have root below it, and below it you have the right subtree, then this is a good state to be in. Why this is a good state to be in? Because first left subtree will be processed, and then root will be processed, and then right subtree will be processed. This is the basic idea. How to do it by code, I'll come to that, but this is the basic idea, that I want to move from this state to that state. Is it making sense to everyone? Why we want to move from this to that state? Right? Okay. But you know, the key thing that you should understand over here is when to print this root and when to move from this state to the other state. So let me tell you one thing. Let's say you have 2 over here. Okay. Let's say you have 2 over here. Now you want to change this thing from here to this thing where you want 3 at the top, which is left subtree of the 2, and then you want this 2, and then you want right subtree. But now moving on and on, moving on and on, if at some stage you have 2 at the top, will you again want to move from this state to that state? The answer is no. Now you would want to print it. Why you would want to print it? Because before this 2 there was the left subtree, and now because 2 is at the top, it means that left subtree has got printed. Correct? And the rule of in-order says first you print left subtree, then you print root, and then you print right subtree. This is the rule of in-order. So it means that whenever you are meeting a node for the first time, whenever you are meeting a node for the first time, then you first push its right subtree, then push that node again, and then push the left subtree. So I'm writing it. If you meet a node for first time, then what you have to do is you have to first, so first you take that node out, and then push the right subtree, push the node, and then push the left subtree. You know, doing so will ensure that you move from this state to that state. Like if you first push 2, and now this is the stack that you're looking at. So let's say you are seeing this 2 for the first time. So you will take this 2 out. After taking this 2 out, you will first push 7, which is the right subtree, and then you will push 2, and then you will push the the left subtree, which is 3. Is this step clear? What to do to the node when it is seen for the first time? Is that making sense? Yes or no? Right? But when you see a node for the second time, when you meet a node for the second time, then all that you have to do is take it out and print. Take it out and print and let it go. So now there are 2 things to understand: how to distinguish between first time and second time, how to figure out whether the node that I am seeing at the top, is it being seen for the first time or second time? Is that making sense? We have to distinguish that. Now, how to distinguish it? You can do that by using a flag. So that flag could be 0 or 1. So what I am going to do now is, okay, first of all, are these 2 things making sense? What to do to a node for the first time and what to do to a node for the second time? Others? Yes, no? Okay. So let's say we have a stack. Okay. In order to check whether a node is being visited first or second time, along with the node, I'll push a flag. So flag 0 means it is being seen for the first time, and flag 1 would mean it is being seen for the second time. So right now the top of the stack is that it is being seen for the first time because the associated flag is 0. So what I'll do is I'll take this thing out. So let's take this thing out. And after taking this thing out, according to this rule, what I'll do is I've taken it out. I'll push the right subtree. The right subtree is 7. Okay. So my first step is to push that 7. Now tell me one thing, when I am pushing this 7, what should be the flag? What should be the flag associated with 7? It should be 0. It should be 0. Why? Because you are pushing this 7 for the first time. Okay. And then the next step is to push the node again. Now, when you push this node again, what should be the flag? The flag should be 1. Why? Because now you're pushing it for the second time. So an important point over here is when you push the node, push it with flag 1. And when you push the when you push the right subtree and the left subtree, push them with 0. Okay, so now after pushing the node with a flag of 1, you will push the left subtree, which is 3, with a flag of 0. Cool. Now you will keep moving this thing on and on and on. So now again, the topmost is 3, 0. You will take 3, 0 out. And tell me, what are the steps? You take that node out. This 0 means that this node is being seen for the first time. So this rule will apply. Now you will push the right subtree. What is the right subtree? The right subtree is 4. So you will push 4. So you have 7, 0, have 2, 1, and you will push 4 with 0. And after that, you will push the node with a flag of 1. The node is 3, which is pushed with a flag of 1. And after that, you will push left subtree with a flag of 0. Left subtree, does it exist? No. So you won't push anything at all. Cool. Now move on to the next step. Now what is the top of the stack? The top of the stack is 3. What will you do with this 3 now? Will first time rule apply or second time rule apply? Which one? This second time rule will apply because now this 3 has a flag of 1. Because it has a flag of 1, it means it is being seen for the second time. So you will take it out and print it. That's it. Now tell me, if you were doing in-order traversal of this tree, the first node that you would have printed would have been this 3 only, right? And you have printed this 3 because it does not have a left child. And if it had, that must have got printed, correct? Yeah, now the top of the stack is 4, 0. This is being seen for the first time, so this rule will apply. So you'll take this 4, 0 out. And after that, you'll push right subtree if it exists. Right subtree exists. So you will push it. So you have 7, 0. You have 2, 1. The right is 6. So you push 6 with 0. And then you push the node itself. You push the node 4 with a flag of 1. And then you push the left subtree if it exists. The left subtree is 5. And you push this 5 with a flag of 0. Correct? Now again, let's move on to the next step. In the next step again, the topmost element of the stack is 5, 0. So you will take this 5, 0 out. After taking this 5, 0 out, you will push the right subtree, but it does not exist, so you won't push. You'll push the node with a flag of 1. So you'll push this 5, 0 back. I'm just pushing it here itself with 1. And after that, you will push the left subtree. It does not exist. Now again, in the next iteration, the topmost element of the stack is 5, but the flag is 1. So you'll take it out and you will print it. So after 3, you will print 5. You know, this is how it will keep going on and on and on. Is it making sense, like how this algorithm is operating? Yes or no? Any questions, anyone? Can you write the code here? Okay, so you can take it as an exercise to just go back from here and try writing a code. So you would now need a stack of what? Should it still be a stack of node star or should it be a stack of something else? Pair. It should be a stack of 2 things, node star and a flag. That flag could be Boolean, like this 0, 1 could be integer, or it could be Boolean, true, false, whatsoever you want. So you need to have a stack of pair of node star, comma, bool. This is what you need. And you will initialize your stack by pushing root, comma, 0 or root, comma, false. And then you have the same logic that while your stack is not empty, you take out the topmost element. Once you take out the topmost element, the first thing that you do is you check whether its flag is 0 or 1. If the flag is 1, just print it because it is being seen for the second time, correct? And if the flag is 0, then follow this rule, correct? Okay, so at least write the pseudo code or something for now, so that when you go back, you are able to write the actual code on your own. Okay, great. Cool. So now, do you feel that using the same sort of idea, you can also do post-order traversal? Yes or no? What change will come? So those of you who are listening attentively, you would realize that in post-order traversal, let's say this root is being seen for the first time. In post-order traversal, you first print the root. You first print the left subtree and then the right subtree, and then you print the root. So what kind of state do you want to go to? Tell me. If you're seeing a root for the first time, you'd want to take this root out. And after taking this root out, you want this root to lie at the bottom. And above it, you want the right subtree. And above it, you want the left subtree. So the only thing that will change is this sequence. How many of you are able to get that? And can you write a code with the changed sequence? It will be a good exercise for you guys to do. Yeah, please do that when you go back from here. Okay, cool. So now I would just change the topic, move on to something else. But before that, as we have been learning trees from past 3 days, I think 3 days, right? Is there anything that you wish to share with me? Any particular problem that you're facing while solving problems, or anything that does not click you so well? We don't have a lot of time right now. I can just give you an intro of the next topic, but before that, let me know if you wish to share something. Are you guys finding the topics hard? How many of you are finding the topics hard? Let's do a quick poll. Yes, no? How many of you are finding it medium? Those of you are finding medium. Yeah. How many are up for easy to understand and all? Okay. Okay, time and space complexity, for that, maybe I would encourage you to take a look at time and space complexity section of Renaissance. It's already there on your dashboard. So if you want to spend time with it, go ahead and spend. Okay. Okay. So now, some of you said implementation. So implementation will become easy when you have the intent to, write the code for every problem, because when you're coding something, it is impossible that you are unable to code it if you have understood the logic. See, while coding, you should know 2 things. First, logic should be crystal clear. And second thing, you should know the language. The second thing is a very cheap thing to know. Language, I mean, how to use stack in JavaScript or how to use stack in Python is super easy to know. Stack Overflow will bombard you with a lot of answers, right? So that is something which you should learn figuring out, and you should try to code it. That's how you learn. I mean, the game is never like you first learn the language and then you implement the problem. It never happens like that. People implement the problems, and in process of that, they get to know about language. Yeah. Coding in JavaScript is okay. It is definitely okay if you are comfortable with JavaScript. Okay. If you're not comfortable, make yourself comfortable, or if you find it too tough for yourself, change your language. Okay, cool. So, so we learned trees because we had learned recursion first. So I would like to cover all the topics whose backbone is recursion. So I would move on to dynamic programming. Okay, it's well known that people say it's the hardest topic or something like that. But when people say it is hard, they internally mean to say that recursion is hard. DP is not hard. See, DP is just a one-line concept. What is hard is recursion. When people say DP is hard, they mean to say recursion is hard. So if you have learned recursion, spend time with it, solve problems, you will be able to follow DP. That is for sure. Cool. So before I start talking about it, can you let me know your thoughts about DP? Like, what is DP? What do you know about it so far? And if you don't know anything about it, you can tell me I don't know anything about it. And then we can get started. Okay, one of you is saying pre-computation or memorization. Okay. Intelligent recursion. Okay, let's talk about it. What exactly is DP? So let's take example of a very simple problem. Okay, the problem is that you ask a person to maybe print the sum of first one natural numbers, and then you want to ask the person to print the sum of first two natural numbers, and then print the sum of first three natural numbers, then print the sum of first four natural numbers, so on and on, print the sum of first n natural numbers. You all understand what natural numbers are? Natural numbers are 1, 2, 3, 4, 5, 6, so on and on, right? So what will be the answer to the first question? What is the sum of first one natural number? So if I list down all the natural numbers for you, I'll get 1, 2, 3, 4, 5, 6, 7, and so on and on. The first natural number is this, and its sum is 1. The first two natural numbers is this, its sum is 1 plus 2, 3. The first three natural numbers is this, its sum is 6, and so on and on and on, right? So this is what I want you to do. Now, what this person is doing is, to answer this question, he starts summing from here to here, and he get 1. To answer this question, he starts summing from here to here, and gets this. To answer the next question, he starts summing from here to here, and gets 6. This is what this person is doing. It means that to find the sum of first 6 natural numbers, he will do sum till here. And to find the sum of first 7 natural numbers, he'll again do a sum till here. What do you think? Is it an intelligent thing to do? Yes or no? It is not an intelligent thing to do. Why? It is not an intelligent thing to do because when you need the sum till 7, then it has an intersection with the sum till 6. So if you already computed it, then what is the need to compute the part from here to here in this thing again? It is not a wise thing to do it. Now, moreover, you see that the solution of this much part is dependent upon the solution of this much part. And this is exactly what was the recurrence relation in recursion also. Like you said, traversal of a big tree is dependent upon the traversal of its left subtree and right subtree. Similarly, you can say that sum from 1 to n is equals to sum from 1 to n minus 1 plus n. Like if I know the sum from 1 to 6, I can just add a 7 to it and I'll get the answer. Is it making sense to everyone? Yes or no? right? Now this thing again, it continues to be called as your recurrence relation. It continues to be called as your recurrence relation. Now, whenever you are writing these equations, you do not mention those things which do not change. Like this one does not make any sense. So I can just write it sum n. Sum n means sum from 1 to n. Similarly, sum n minus 1 means sum till n minus 1. So this is the equation that I can write. And once I write this equation, I can just use it for all my purposes. Okay. Now, as I said, for every equation that you write, there is a base case. So this equation will apply for all the values of n which is greater than 1, but it will not apply for n equals to 1, because when you put n equals to 1, you will get sum of 1 equals to sum of 0, and sum of 0 is undefined for me because I am only considering the space of natural numbers. Okay, so there would be a base case for n equals to 1. If n is 1, then sum of 1 is equals to 1. Correct? So now if somebody has to solve this problem intelligently, he would say, let me have an array, and in that array, I would do sum of 1 equals to 1. And then I would write a loop which computes the sum of first 2, first 3, first 4 till first n natural numbers. So I goes from 2 to n, and using this formula, I can say, just substitute I in place of n. I can say sum of I is simply equals to sum of I minus 1 plus I, right? So that way, you will get an array where sum of 1 will have the sum of first natural number, sum of 2 will have sum of first 2, then 3, then 4, and so on and on and on. Does it make sense how and why this code is correct? Anyone who can talk about the time complexity of this code? Order n, right? You can see that there is a single for loop which is running for n times and getting a job done. Okay. Now I want to solve the same problem recursively. It's just that the problem is a bit different. The problem says that, hey, print the sum of first n natural numbers. So if your n is equals to 3, print 6. Can you write a recursive code which, given a number n, prints me an integer, and that integer is the sum of first n natural numbers? How many of you can write that recursive code? Super easy to write. Everyone do that. Once you have written, you can type yes, and you can also share your code. Yeah, so one of you has written it already. Now let us just take a look. So, I can have a function func. This function takes an integer n, and its responsibility is to give me the sum of first n natural numbers. So it will return an integer. Now, what is the first line in your recursive program? Base case. And what is your base case? Look at the left side of the board. It says if n is 1, return 1. Good. So it says if n is 1, return 1. Otherwise what to do? Otherwise you return sum of n minus 1, which you can get by recursively calling this method for n minus 1 and add n to it. If you look at this approach and that approach, what is the difference between them? The first difference is this is iterative and this is recursive. Iterative and recursive are just English words, but fundamentally, this approach is a bottom-top approach. Why this is a bottom-top approach? Because it does not attack n directly. It first attacks sum of 1, then sum of 2, then sum of 3, then sum of 4 till n. So it kind of crawls its way from 1 to n. So it is bottom-top approach. And this approach is a top-bottom approach. Why top-bottom approach? Because it directly attacks n. It first attempts to find sum of n, and for that it realizes, oh, I have to find sum of n minus 1. And then it realizes, hey, I have to find sum of n minus 2. So on and on, it goes till sum of 1. So the function fn calls fn minus 1, which keeps calling. The return anyway happens from bottom to top only, but the way it attacks is from top to bottom. So recursive approaches are top bottom and iterative approaches are bottom top. Is it clear to everyone? Like what is the meaning of top bottom, bottom top, and how they are different? Yes or no? So I'm telling you these jargons today because they'll frequently be used when we talk more about dynamic programming. But for now, I'll just keep this much for you. And there is an essential homework for you guys to be able to attend tomorrow's class. When you go back, just open your dynamic programming dashboard and just go through the first 4 or 5 lectures. They are super easy to understand and they are just the fundamentals. So if you come after watching them, then you will enjoy the class on DP. Can you guys do that? Yeah. Okay. Cool, then let's meet again tomorrow and continue our learning journey. Okay. Bye everyone.